All right, welcome. This is Trig. This is 9.4/9.5. We're going to be learning about trigonometry ratios. First thing to do is to figure out what the heck that is. What is a trig ratio? Well, it is the relationship that compares side lengths with angles. It's about that. Kind of. Now, when we're talking about relationships with side lengths and angles, what are we talking about? What the heck is this? What we're really talking about is sine, cosine, and tangent. You may have heard of these before. Apparently, in some classes, these are the forbidden buttons on your calculator, the ones that you're never supposed to touch. But this is when we're going to be able to touch them and use them, because we're going to be using them for the rest of Chapter 9, and you should just get used to them in general, because more often than not in math, you're going to have to use sine, cosine, and tangent. That being said, one thing to note about sine, cosine, and tangent is the fact that when using them on your calculator, it's very important to know what mode your calculator is in. Now, I am unprepared today. I am at home. Calculator's at school. My notes are at school, so I'm freeballing the notes today. Good thing that this is after I taught a few times already today, but it's okay. Your calculator needs to be in degree mode. If you are unsure of how to turn your calculator in degree mode, ask me, please, when you get to school. In short, if you press the button that is labeled mode, that is pretty much right next to the second key, the blue button on your calculator, you'll get a screen of a bunch of settings on the calculator. But in specific, the settings that we're focusing on is the one that has radians and degree. On default, the calculator is going to be set to degree. So you're going to have to hit the arrow key, and you want the black box to be around the degree sign. You press enter, and then that's going to fill in that black box. And then you can hit the clear button, and now your calculator will be in degree mode. You know what? This is a pretty good picture demonstration of it. So if you did not follow this and did that process, when you come to school, ask. I'll show you. Anyways, with that out of the way, we're going to actually start working with sine, cosine, and tangent and seeing what we develop with them. Now, I have 3 triangles set up now in our notes. In your note packet, you only have 1. I'd recommend working with 3 because we can start drawing everything out, and it's just going to be a lot nicer if you work with 3. I'm going to be real. I have to go get another color pen. I don't have my pens right next to me. They're in a cup. Actually, they're all over the place in my room. Get some other colors. Ugh. I don't want to use black because I already wrote that. Hey, I pre-prepared today. I had to write all this stuff out. Anyways, what is sine? Also, I'll just label these right now. They're all the same triangle. We're just using them 3 times. It's going to be nicer so it's not all colorful. One triangle. Anyways, what is sine? Well, sine, it's trigonometry ratio. I'm not even going to try. Sine, and I'm going to put a placeholder value there. In trig, when working with trig, in specific with working with angles, there is the preset angle that we kind of default to for our x for trig. We call it theta. So I'm going to have sine of theta is equal to the opposite side. over the hypotenuse. This is the ratio for sine. Now, when looking at sine of A is this theta. A is our angle that we're looking at. So when looking at angle A, I guess we'll use blue, I guess, for A. Going onward, I'll use a different color. For A, what this means, since I'm trying to find the sine of it, which is the opposite side over hypotenuse, I'm going to start at angle A, and I'm going to go to its opposite side length. So going opposite of that angle, I'd hit 3. So that means my opposite side is going to be 3. And I can put that over the hypotenuse. Our hypotenuse is the angle opposite of this right angle. In our case, it's 5. So the hypotenuse is 5. So that means sine of A is 3 over 5. I'm going to do this right now and state that the hypotenuse is 5 for each one, because this triangle is the same. The hypotenuse is always opposite of that right angle. So there you go. Sine of B. Now, obviously, we did sine of A. We can also work with other angles. So that's why we're doing sine of B. So starting at B, I need to go to the opposite side of B, getting 4. And 5 is my hypotenuse still. It is still opposite of that right angle, so we have 4 over 5. So, sine, its ratio is opposite side over hypotenuse. Awesome. Moving on to cosine. What is cosine? So, cosine of theta, just put in a placeholder angle in there. The cosine of theta will be the adjacent side over the hypotenuse. I will make a quick note. The adjacent side cannot be the hypotenuse. They cannot be the same side length. The hypotenuse, if we already have one and it's labeled the hypotenuse, it will only be the hypotenuse. It will never be the adjacent side. Because remember, adjacent means right next to. Or, yeah, right next to. And looking at angle A. Oh, crap. I meant to use a different color, not green. I want to use green for B. Let's use... we're going to use orange. Just scribble over. Looking at angle A. We see the hypotenuse is right next to angle A. But... Since it's already labeled as the hypotenuse and it's the biggest side, we can't... This ain't going to be our adjacent angle. Our adjacent side. The adjacent side would be the other side length. In this case, angle A, side AC with the length of 4. So 4 will be my adjacent side. Then it's over hypotenuse, which is 5. Cosine of B. Looking for my adjacent side length, because that is on my top. That's my numerator. That would be the side BC with the length of 3. That's over my hypotenuse, which is 5. So cosine is adjacent side over hypotenuse. I'm drinking some Gatorade. Very orangey flavor. I like my orange flavor. I have a 4-pack of Gatorade. Gatorade powder. I have to say, I think I like the blue one the best. Orange is probably number 2. Then it's fruit punch and grape. I do not like grape flavored things. Anyways, what's tangent? Speaking of tangent, I'm going off on a tangent. Tangent of theta is going to be the opposite side length over the adjacent side. So this is how tangent is set up. We're going from the opposite side to the adjacent side. No hypotenuse is in play here. only the opposite side over adjacent. So that means when working with tangent of A, this angle right here, I'm going to start at angle A and go to its opposite side. And that's 3. And that'll be over its adjacent side. Remember, adjacent side is different from the hypotenuse. So in this case, it's 4. So my tangent of A should be 3 over 4. Looking at B, starting at angle B. Going to its opposite side, I hit angle 4. I hit 4, so 4 is my opposite side length. And then BC is that adjacent side, with 3 being its length. So I have my tangent of B is equal to 4 over 3. Not too shabby, I must say. So, recapping. Sine is equal to the opposite side length over the hypotenuse. Cosine is equal to adjacent over hypotenuse. Tangent is equal to opposite side over adjacent. That's a lot of memorization, I must say, but there's a clever thing we can say in order to make it a little nicer to remember. Looking at the front of your notes, you might have seen Squidward saying Soka Toa. It's an acronym. What does that acronym stand for? Well, let's fill it in. S. That is sine. O. Opposite. H. Hypotenuse. Oh, would you look at that? That is the sine ratio. Cosine. A. Adjacent. And H. Hypotenuse. Oh, would you look at that? That is our cosine ratio. And then I think we are getting the picture here. TOA is going to be our tangent ratio. So sine opposite of hypotenuse. Cosine adjacent hypotenuse. TOA tangent opposite adjacent. There you go. Woo! Free bird. Yes, sirski. All right. Easy way to remember if you don't want to actually memorize the formulas. Knowing the acronyms helpful. So in a pinch, you can always write out SOGATOA on your test, and you should be okay because I'm not giving you the ratios on that test. Anyways, we're gonna use this diagram to help us solve for sine, cosine, and tangent. Now I do not have anything labeled yet, but now we do. There we go. We have some labeling that I just did. And now we can find sine, cosine, and tangent of SRT. Well, S and R. So looking for sine of R, starting at angle R, I can go to its opposite side. Because remember, sine is opposite over hypotenuse. That is 16 over the hypotenuse, which is 65. Now, when doing these problems, you're going to end up having a fraction. What I want you guys to do as well is to write this fraction in decimal form. But what I mean by decimal form is that I'm going to have to pull up a bit. Decimal form. Oh my God, it's so white. There we go. Decimal form. So I typed this into my calculator on my internet because I do not have one at my house right now. It is currently sitting on my desk at work. But if you type in 16 over 65, you end up with the decimal like that. What I want you guys to do is to give me the first 4 decimal places. So looking at our number, we have 2, 4, 6, 1, 5, 3, 8. So I want the first 4 decimals, so that means I want 0.2461. You do not have to round. This is called trunking. Just shortening your answer like so. No rounding, please. This is going to be useful for when we are actually plugging in stuff inside of sine. But for right now, give me these 4. Oh, that's a little better. Going mobile today. Take it off the tripod. You guys, I should probably show you what this setup I'm working with right now. It is not the prettiest thing in the world. All right, so we got sine done. I want to use a different color for each one. We'll use orange for cosine. So doing cosine of r, I'm looking at the opposite or the adjacent side, which is 63 over the hypotenuse, which is 65. Doing 63 divided by 65, I'd end up getting our decimal 0.9692. Truncate it off at that 4th decimal place, and then we'll use green for tangent. Tangent is opposite over adjacent, so going to the opposite side, I'd end up with 16, and 63 is my adjacent side length from angle R. So that means I'd have 16 over 63, which is 0.2539. That is my decimal. All right, going to the sine of S. So starting here, I need to go to my opposite side length. So pew, going all the way down. We end up at 63 over my hypotenuse, because sine, opposite, hypotenuse. So I get 63 over 65, which is 0.9692. Going to cosine of S, I'm looking at my adjacent side length, which is 16 over the hypotenuse, because cosine adjacent hypotenuse. So I'd have 16 over 65. That gets me my decimal of 0.2461. And then I have tangent of S, which is the opposite side, which is 63 over 16, because we have our opposite side length from angle S, which is 63, and then our adjacent side length, which is 16. And that will give me the decimal of 3.9375. Okie dokie. Looking at what we just found for sine, cosine, and tangent, what are some things that we notice? First things first. We have that the tangent of r is a flipped version of tangent of S, seeing that we have 16 over 63 and then 63 over 16. Interesting. Our second thing, we can also note that the cosine of S is the same as cosine of R. I mean sine of R, not cosine of R. We can also note that the sine of S is the same as the cosine of R. This plays into something we can work with going forward. That being some complementary angle business. Now, when going back and thinking about complementary angles, and let's just take a look at what we're working with, like in general with right triangles right now. Complementary angles. Remember what complement meant back in whenever we used it? Like unit 1, unit 2, 3, 4, almost every unit. It's two angles that add up to 90 degrees. Complementary angles, when we're working with right triangles, are the two angles that are not the right angle. these two angles add up and equal 90 degrees. So, when we are looking at, especially taking a gander at this, what we see down here, that the cosine of s is equal to the sine of r, and the sine of s is equal to the cosine of r, they are considered complements of each other. In the words of complementary angles, the sine of an acute angle is equal to the cosine of its complement, and the cosine of an acute angle is equal to the sine of its complement. What does this mean? Well, let's take a gander. Let's let A and B be complementary angles. Complementary angles, that means A plus B will equal 90 degrees. Then the following statements are going to be true. Sine of A, we can set that equal to cosine of 90 degrees. So this 90 degree minus angle A will equal angle B. Let's label this as angle A and B to help us visualize it. I'm off camera. So the sine of A, looking right here, is equal to cosine of 90 degrees minus angle A will get us to B. It's almost like doing 90 minus A will get us to B. Same can be said on the cosine version. Going to cosine of A, that's equal to sine of 90 minus A. Doing 90 minus A will get you the sine of B. And same thing can be said for B. The sine of B is equal to the cosine of 90 minus B. Doing 90 minus B will get us to angle A, which cosine of A. In physics, you can kind of work in tandem with cosine and tangent and get the same value. We did that with we just did that right now. It's very interesting. It's very freaky properties that these trig ratios have, and we're only scratching the surface of it in geometry. In other classes, you can get more in depth about it, but we're only touching the surface. So that means we can convert these statements, cosine of 63 and sine of 75, into entirely different functions. Like I can change this to the sine. How am I going to do that? Well, let's follow one of these steps. I mean, it doesn't matter which cosine one we follow, but let's just say we're doing cosine. Let's follow this one when I'm changing this function, cosine of 63. So I want to change this to a sine function. So in order to do that, I got to take this cosine. First, I got to change it into sine, parentheses, 90. This 63 is acting like this A. So I got to do 90 minus 63. And then that will get me my sine, which is going to be 27. And it doesn't just work for this way. We can go the opposite way. Doing sine of 75, I want to change it to the cosine function. So that means this sine of 75, I want to change. To change that, I do cosine of 90 minus this angle that I have, 75. And that will equal the cosine of 15. So also you can think of it as, it's almost like shifting something into a different language. Like say you have, let's just say I'm translating a word from English to Spanish. It's the same word, but moving into a different language, but they mean the same thing. You can think of it that way. I'm writing it in sign language instead of cosine language, if that kind of helps illustrate what this process is going at. It's not too bad. One fun fact about trig functions as well. Not only do they have relationships with themselves and angles, but it's the fact that we are able to find missing side lengths. Woo! Missing side lengths! Yay! So, we're going to do that. Now, this is where not having your book is, or your notes, sucks, because I have to make these on the spot. So, I'm trying my best. I know this one is like an actual one that we have to do. So, I want to try to find out what the value of x is from this function. Now, you guys, personally, need to work on your problem solving skills and trying to piece together what you're working on or working with. This is when seeing SOHCAHTOA comes into play and kind of helps you try to figure out what the heck you need to do. So the first thing that you should do is key in on the angle that you have and work off of that angle, because this angle and side length that you have is going to determine which function you're using, whether it's sine, cosine, or tangent, and then that determines what ratio you use. So looking at this angle you have, I have 53. Now, let's just try to go to the nearest side length that I have that's an actual number, that being 12.3. How am I going to get to 12.3? Well, I'm going to go directly to that side. Now, this motion that I did from the angle to the side length, it's like I'm going to the opposite side. That means 12.3 would be an opposite side length. We know x is our hypotenuse because it is opposite of that right angle, so I can label it as my hypotenuse. Okay, I think we see the picture. I have an opposite side length from my angle, and I have an hypotenuse. From these three ratios that I have set down, I know that sine deals with opposite and hypotenuse, so that means I'm going to be dealing with a sine function using opposite over hypotenuse. Cool. Now I can fill in what I have. So now that we're working with sine, I guess I'll put theta here since we've been working with theta. Now we fill in what we know. I know this angle right here is 53, so that means I can put sine of 53 right here. That's equal to the opposite side, which is 12.3, over the hypotenuse, which is x. And now I can solve for x. Doing x times x, I'd end up with x times sine of 53, which is equal to 12.3. And then I divide by sine of 53 to get x by itself. And you want to divide by the whole function. And what, also, just noting right now, do not take the sine of 3 at all. You just move it around. What I mean by this, and I'll type it out and show you on the computer. Where's my mouse? Sine of 53 degrees. All right. I guess this is a good way to see. All right. So I want you to type in your function like this on your calculator, not finding the actual sign yet. And in the calculator right here, it says convert from radians to degrees. I'm hitting that because I want the actual degrees. Uh-oh. Do that. Evaluate. Oopsie. There we go. Boop. There we go. This is my expression that I want. 15.4. It's already in degrees. And then, yeah. So, it was 15.4. I remember it. So that means x is 15.4. Get me to the nearest tenth for your decimal place. So 15.4. All right, we'll do another example. Let's say we have a triangle that looks like this. Okay, let's say we have an angle of 77, because I like writing sevens, and we have let's say that we are working with 9.5, and I want to find out what y is. I don't know, I'm trying to work on this on the spot. I'm sorry. Anyways, this is the information that I have. Let's try to work with it. So, I have 77. This is my angle. I got to work off of this. I do have a number value, but it is currently my hypotenuse because it is opposite of that right angle. What I do know, though, is that I do have another value, which is y. Y is right next to my angle. So that means my y value is going to be adjacent. Looking back at our list of what the heck can we do, I have an adjacent side and a hypotenuse, so that means I'm using cosine. So that means I'm doing the cosine of theta is equal to adjacent over hypotenuse. And then I can start plugging in my information, like cosine of 77 will be equal to y over 9.5. And now I can get y all by itself, taking or multiplying by 9.5 on both sides. And now that is pretty much all I'm doing. So let's do 9.5 times cosine of 77. And that will get me 2. A y is equal to 2.1. Around. One more example. We have boom, boom, boom. I have this angle right here. Angle. We'll say this is 41. And I am working with I want to find z. And I have 15.8. So, looking at my angle first, because this is what I know, how I can set up things. And then, from this angle, I can start working with my side lengths. Seeing that I have a number value right here, to get from my angle to my number value, I'm going to have to go across this whole angle to get to that side, which means that this is going to be the opposite side to this angle, 41. So this is the opposite. I also have this z, which I'm trying to find, right next to 41, so this is adjacent. So that means, looking at my list of fun values, I have opposite and adjacent, so I'm working with tangent. So that means I will have the function tangent of theta is equal to the opposite side length over adjacent. So plugging in what I know, I have tangent of 41 is equal to 15.3 over z. Getting z all by itself, I'd end up with z times tangent of 41 is equal to 15.8. Dividing by tangent of 41, I will get a z that is equal to, well, let's find out. What are your guesses? If I got I'm going to say it's going to be like it's going to be in the 20s. I bet it's going to be in the 20s. 18.1. So it's 18.1. That's my z. It's around 18.1. It's not too bad working with this. You just got to make sure that you're working in degree mode, not radians. All right. Because I don't want to cut the camera because I'm lazy and I don't want to reduce this film down. I need to go to Google Drive. See, the fact that I did not have my notes, I cannot finish out finish out this section. So hopefully I can find the packet filled in somewhere on the Google Drive. It is not on the Google Drive. Maybe it is. Maybe it's going to be filled in. You know, have optimism. Maybe it is filled in. Ooh. Nope. Is it in hers? Nope. Hold on. Have faith. It's right here. Please. It's not. Oh my god. I want to... Oh, wait. Hold on. Hold on. We're cooking. We're cooking. Hold on. I know what to do. I'm pull out the book. Oh my god. See, it's like I have everything already set out. It's just like... Alright. Next part. This goes into day 2, by the way. Angle of elevation. What is angle of elevation? It is formed by a horizontal line and a line of sight up to an object. So this is a definition from the book, which does not help you guys at all. What is angle of elevation? Like, if I had to draw a picture out, let's just say we start on a flat surface. This is when something rises up from that flat surface. So, like, if I have my finger flat on the ground like this, the angle of I can create an angle of elevation by raising my finger up like this. Let's just say I raise it up to here. This angle right here would be that angle of elevation from the horizontal line. Let's put this into practice with example 3. We have Cristiano Ronaldo is playing football in the game of his life. He's about to kick the game-winning goal from 36 feet away from the goal. When he kicks the ball, it leaves the ground at an angle of elevation of 13 degrees. Will the ball be able to go into the goal if it's 8 feet tall? Okay. So, our first thing and first action is to draw a diagram. And when I mean draw a diagram, guys, I mean you need to legit draw this out. You cannot do this just straight up, and you need to be good at drawing diagrams. You guys are kind of poo-poo at doing it, and I saw it today when we were doing the unit story. So, we have Ronaldo right here. He is 36 feet away from this goal. This goal, and we'll make it a goal, is 8 feet tall. But I kick the ball at an angle of 13 degrees. I don't know how high this ball is going, so I want to know if it's going to go over this 8-foot goal. So my initial goal is to find out how high this ball is going. So it could be higher than the goal, we don't know. But looking how I'm kicking and what I'm just working with in general, I have an adjacent side length with me. And it has a legit value to it. So that means looking at SOHCAHTOA, our properties, our ratios that we're using, sine is not even in the question since we have a legit value for an adjacent side. We have 63. I said 63 again. I meant 36. We have 36. The other thing to mention that we do know of, or what we kind of want to know, is how high this ball is going. Now, we know the height of the goal, which is 8 feet, but I have no idea how high this goal is going, how high the ball is going to go, whether it's going to go in the goal or not. Oh my God, it bled through. So if I went from this angle all the way to this goal, which is 8 feet tall, this would be the opposite side from this angle. So that means my height of the ball that's getting kicked will be the opposite height, which is what I'm trying to find. I already said this was adjacent. Looking at SOHCAHTOA, I have opposite and adjacent. That means we're using tangent. So we're using tangent of theta is equal to the opposite side length over adjacent. Now, what are we trying to find? We're trying to find how high I'm kicking this ball, whether it's going to go into the goal or not. So we have tangent of 13 is going to be equal to our height of this ball. I'm going to put h for height, and then our adjacent side, which is 36. I got to get 36 to the other side to get h by itself. So we'd have 36 times the tangent of 13, which is equal to h. Plugging that into your calculator, which I will do in a second because now I got to pull it up. 36 times the tangent of 13, that will get you a height that is around 8.13 feet, which is bigger than the goal. So that means Ronaldo is kicking over this goal, which means the ball misses the goal. Poor Ronaldo. If only he was Messi, then maybe he could kick the goal. I'm not going to get into the soccer politics. Oh my God. I said football and soccer. Oh, you guys are going to kill me. All right. Should I just make up my own definition for angle of depression? Angle of depression, same gist of angle of elevation, but it's going downward. Example, given this line right here, and given if I put my finger right on the line, the angle of depression would be going from a horizontal line and moving my finger downward. It's the angle that opens downward. That would be the angle of depression. So it's like me looking down at a desk. That would be an angle of depression with like my head tilting down. That's an angle of depression. If we want to write a legit definition of it, we can. It's formed by a horizontal line and a line of sight down to an object. No better way to practice this is with an example. So let's say Mrs. Rose, instead of Mr. Rose, is a lifeguard looking down at a swimmer in the pool. Your line of sight forms a 55 degree angle of depression. You are 10 feet up on your seat. How far away is the swimmer from the base of your lifeguard stand? Drawing out a picture. I am right here. We are sitting pretty. Miss Rose is sitting pretty on a lifeguard stand, which is 10 feet tall. I have a swimmer swimming down here. Cool. From my line of sight, I form an angle of depression. That is an angle of 55 degrees. And I want to try to find this distance. I drew this so horribly. Drawing it in a different picture. Or kind of like drawing out what I need to work with. 10 feet. I'm trying to find this. What? Oh God, this doesn't even work either. 10 feet. I'm trying to find this. 55. Goodness gracious. I gotta find what X is. Funny enough, we're given kind of the same basis as what we just worked with the fact that I don't have a hypotenuse, but I do have an adjacent side length because 10 is right next to this 55, and this X is the opposite side length to 55. So that means I'm working with tangent again. Doing tangent of theta is equal to the opposite over adjacent side lengths. So that means I can do tangent of 55 is equal to the opposite, which is X over 10. Moving 10 to the other side, I'd have 10 times the tangent of 55, which is equal to X. And that will give me a value of, I have no idea. An X that is equal to 14.28 feet. That's how far away the swimmer is. I drew that picture so badly, guys. I'm sorry. That was horrible. I usually am good at drawing pictures, but not today, apparently. All right. Those two problems, angle of elevation and depression, are just more wordy problems. It's a upgrade to what we have been working with story problems. I really, really, really hope that you guys take your time and actually draw out these pictures and put effort in drawing out the pictures because it's going to help you so much. Now, to step aside for a quick second, this stuff covers, this isn't like super duper important, but it's stuff that it will be useful to recognize, in the thought of, hey, this might come up. Like, yeah, this might come up. And it's about special right triangles with their sines and cosines and what that means and what it states. So if you see a 45, 45, 90 triangle and you need to work with the sine and cosines, there are specific values you get. And these relate to stuff that you work with further on in math. But just to write out what they are. For all of cosine and sine, we are working with the square root of 2 over 2. How do we get the square root of 2 over 2? We'll do an example of it. So let's just say we're going to do the sine of A. So the sine of A is the opposite side length over hypotenuse. Going to the opposite side, I'd get 1, and the hypotenuse is square root of 2. So that means sine of A is equal to 1 over the square root of 2. I don't like the square root of 2 in the denominator, so I got to multiply by the square root of 2 to the numerator and denominator, getting me the square root of 2 over the square root of 4, giving me the square root of 2 over 2. That applies for everything. And then tangent is the side length 1 over 1. And that just gets 1. Because it's opposite over adjacent for tangent. So you just get 1. Nice and easy going. For 30, 60, 90s, there are two things that play out. One, if we look at sine of m, looking at sine of m, it is going to this 1 right here, and the hypotenuse is 2. So we have 1 over 2. Going off of our complements of our angles, sine of m is going to be the same as sine of p. So this is going to be 1 over 2. Well, finding sine of p. I meant cosine of p. Finding sine of p now, I need to go to the adjacent side, which is square root of 3. And that will be over 2. Using the complement, sine of p is the same as cosine of m. This is also square root of 3 over 2. We can find the tangent of these, but it is not going to be necessary. But this stuff comes up in like algebra 2 and pre-calc. And if you do get asked a question like this, especially with 45, 45, 90, knowing these off the top of your head, you're pretty good. You're set because these are easy to remember. But you don't have to worry about remembering them. It's just something that's interesting and that shows up later on in your math journey. But that's it. That's all of 9.4 and 9.5. Good riddance. My God.